Good morning, good afternoon, good night. I'm Jiacheng, a PhD student at the University of Michigan. Today I'm going to talk to you about something interesting but not well explored in our community, which is debugging in the new world of reconfigurable hardware. We are all programmers, and unfortunately, we all write some bugs in our life, which is completely normal, and what we need to do is to fix these bugs before being fired. And if we can fix them, there's nothing to be afraid of. Obviously, debugging is painful and brings us a lot of headaches. But for most software developers, it's usually not a big deal, because software is patchable and we can simply release a new version next week. And most importantly, we do have some cures for our headaches. The cure is debugging tools. Previous researchers in the systems community have developed a bunch of tools to help software bugs, such as Vagrant, Thread Sanitizer, Repeat, etc., etc. And there are also a lot of tools still being developed and published in each SOSP, OSDI, and ASPLOS. It seems like our life is moving towards a good direction and software developers now have fewer headaches. On the other hand, hardware is not patchable. Once a bug is baked into the silicon, it's there forever. There's no circuit-level patch, and there's also no fancy tools to help on-chip debugging. Having a bug in a chip also means a recall, during which the circuit vendor will lose tons of money. As a result, people tend to avoid the bug instead of fixing a bug after it occurs. People will test the silicon in a pretty crazy way, and they will also use some labor-intensive formal methods to prove some important properties of the hardware implementation. And both these methods are pretty expensive. So this is a figure about the level of headaches caused by debugging. The right side is silicon, which is not patchable, and there are no debugging tools. The left side is software, which is patchable, and there are a bunch of debugging tools. Actually, in the recent few years, we are seeing the merging of these two worlds with a wide adoption of FPGAs. FPGAs allow people to deploy hardware designs without a silicon fabrication, and the deployed design is always patchable with a simple reconfiguration. FPGA is definitely hardware, because the accelerator design describes the circuit and is implemented in Verilog. This also means that the existing software debugging tools cannot be directly applied on FPGA. However, FPGA is also similar to software, because the accelerator runs on top of a chip, and you can always patch the accelerator after deployment via a simple reconfiguration. So what does that mean? It means FPGA already enables the fix and patch debugging flow for hardware. Why not go one step forward and try to adopt software-like debugging techniques for FPGAs? Currently, the most common way of on-FPGA debugging is to allocate a buffer on the FPGA and selectively record the values of some signals over a limited time range. Developers usually need to carefully select these signals and time range to avoid a huge resource overhead. Another approach is to manually develop some debugging logics for the accelerator on the development, which exposes a bunch of internal states of the accelerator. So as we can see, these things are really basic supports and are not easy to use. Obviously, they are not our favorite style of debugging. In fact, according to recent research, 83% of FPGA projects have bugs in the first production run, which is 13% higher than ASIC projects. And 70% of FPGA developers think the current debugging flow should be improved. To build better debugging tools, the first thing we need to do is to have a better understanding of hardware bugs. And we also need a nice test bed in which we can reproduce some bugs easily and test the tools. So in this work, we first survey and classify existing hardware bugs to understand common causes and symptoms. We then build a test bed in which some bugs can be easily reproduced. And finally, we use the classification to guide an exploration of the state space of potential FPGA debugging tools, and use the test bed to test the tools we build. In particular, we found that there are 3 classes of hardware bugs, which are data misaccess bugs, communication bugs, and semantic bugs. Interestingly, these 3 classes roughly map to the 3 types of software bugs identified in previous research. Data misaccess bugs are similar with memory bugs. Communication bugs are similar with concurrency bugs, and both software and hardware have semantic bugs. The debugging tools we build range from the simplest printf to some more advanced dynamic analysis, and they are all built with on-FPGA testing in mind. Now, we will first talk about our classification result. A data misaccess bug occurs when accessing data without the proper consideration of the size, endiness, bit index, and other properties of the data. Data misaccess bugs can be serious and lead to catastrophic failures, such as an unexpected paper rejection. An example of data misaccess bugs is a buffer overflow, which is something that everyone is familiar with. To have a buffer overflow, you need to have a buffer first, and you also need to access a buffer with an index that's too large. However, a hardware buffer overflow is pretty different from its software counterpart. A software overflow will access the data outside the buffer because from the perspective of the memory, the access is still valid and there's something outside. On the other hand, everything on the hardware is statically allocated and there's nothing outside. So as a result, a buffer overflow in the hardware is usually a warp round and will access data inside the buffer. The second class is communication bugs. A communication bug occurs when 2 hardware components fail to communicate with each other properly. Examples of communication bugs include a hardware module sending data to a consumer who is busy on something else, or a human being talking to a cat who is busy sleeping. Or a communication bug can also occur when a data signal is not synchronized with its control signal. In the following code snippet, response is the output signal we care about, and the response valid indicates whether the output is valid. Assuming the input comes in the first cycle, then at the second cycle, the input propagates to buff response and the response valid. Only at the third cycle does the input reach the variable response. As we can see, the response and the response valid signal are not synchronized, causing a signal asynchrony bug. The third class is called semantic bugs. A semantic bug is generally a wrong implementation. It's like someone asks you to write a hello world, but you end up implementing something else. An example of a semantic bug is API misuse, which is similar to passing the wrong parameters to a software function. From the naming of this module, it seems like the developer wants to see whether A is larger than B. But if the variables are passed to the module in the reverse order, the module will calculate whether B is larger than A instead. We definitely have more examples and subclasses. For this information, please read our paper. In addition to the survey and classification, we provide a test bed consisting of 20 hardware bugs. We ensure that each bug can be reproduced in a push-button manner with Verilator, which is an open-source Verilog simulator. And you can find the testbed in this GitHub repo. The testbed is officially evaluated in the artifact evaluation, and we got all the 3 badges: available, functional, and reproduced. So based on the study and the testbed, we are able to explore the design space of FPGA debugging tools. We first designed a simple and fundamental tool, SignalCat, to provide unified logging functionalities for simulation and on-FPGA testing. We then demonstrated how we can use SignalCat to build more complex debugging tools, including tools that use static analysis and even dynamic analysis. Let's quickly recall what we have and what we want to debug on an FPGA. Traditionally, if we want to debug on an FPGA, we'll allocate a buffer there, and we can feed a few signals to the buffer to record them. And we debug based on the trace provided by the buffer. This is something we have to use, but we probably don't like. On the other hand, we know what we like is printf. Programmers love print-based debugging. People use these statements everywhere, like printf in C and C++. Similar statement is even available in Verilog. However, in Verilog, it only works in simulation. The key idea of SignalCat is to enable printf for on-FPGA scenarios by transforming Verilog's display statement to something provides on-FPGA recording. So we have a hardware module, and the SignalCat will scan the code for display statements to infer the data that developers want to record, and also reason about their trigger conditions. So here, as you can see, A is a variable we want to record, and the recording should only be triggered when reset is false and A valid is true. SignalCat uses this information to generate an instance of the recording buffer we mentioned before and configure it to only record when the display is triggered. With this method, SignalCat provides similar logging capabilities in simulation and on an FPGA, and also eases the development of other debugging tools. Developers of debugging tools can simply generate a display statement and let SignalCat provide platform-agnostic data recording. For example, the rest of our tools all invoke SignalCat when data recording is necessary. Future researchers can also use this method in their own debugging tools. The next three tools are similar. They all target at generating debugging logs and providing useful information to the developers. The FSM monitor identifies finite state machines in the hardware design and generates the trace of state updates. The dependency monitor identifies the dependencies of a user-specified signal and trace their value change. The statistics monitor generates counting logics for a user-specified event. As I mentioned before, these tools all use SignalCat for log generation. LossCheck is a more complex debugging tool that involves dynamic analysis. It is used to localize data losses, which is a symptom we observed in many bugs in our testbed. A data loss is that a packet mysteriously disappears during circuit execution. When a data loss occurs on the FPGA, it's really hard to be manually localized. To understand what is a data loss, we need to abstract a hardware design as a directed graph. In this graph, each vertex is a register, and each edge is a conditional propagation that may or may not happen at each cycle. The occurrence of the propagation is controlled by a condition that can only be determined at runtime. A data loss involves a vertex and an edge. If a vertex holds a valid value and the valid value does not have a chance to propagate to someone else before data propagation occurs in an incoming edge that overrides the value of the vertex, a data loss will then occur. In this example, if the register originally contains value 1 and is never propagated, the value will be overwritten by 2 and the 1 will disappear. So in English, a data loss is that a valid value stored in a register does not propagate before the register is overwritten. As a result, a data loss can be detected by asking a few questions for each register we care about in each cycle. Is the register holding a valid value? Is the value propagated? And is the register being overwritten? LossCheck can automatically check data loss by answering these questions, and it answers these questions by instrumenting the circuit with a small piece of checking logic for each register we care about. To use LossCheck, developers need to specify a data path they want to analyze. They can specify the data path by providing an input register and an output register, and the LossCheck can automatically determine the data path with some static analysis. Other than the input register and the output register, the user also needs to specify the valid signal of the input register because LossCheck will use it to determine whether a value is valid. Then, LossCheck will instrument the data path with some meta variables which answer the questions we mentioned before. Once a data loss is detected, LossCheck can report its location to the developers. So to sum up, we provide a survey and a classification of hardware bugs from open source projects. We built a testbed consisting of 20 reproducible bugs, and we designed 5 hardware debugging tools from some basic ones to some more complex ones with static and dynamic analysis. The artifact of this paper is available via this link, which includes the testbed and the debugging tools, as well as some instructions and scripts. The artifact is evaluated in the artifact evaluation, and we received all the 3 badges. Thanks for watching, and if you have any question, please feel free to reach out.